Thevenin's theorem is an important tool in electrical engineering. It says that any linear circuit can be modeled mathematically as a much simpler circuit consisting of a voltage source, VOC, and a single resistance, RTH. VOC is called the open circuit voltage and RTH is the Thevenin resistance. Thevenin's theorem relates the voltage, Vx and Ix at the terminals of this circuit to VOC and RTH through this relationship. So the terminal voltage, Vx, is equal to the open circuit voltage, VOC, plus RTH times the current into those terminals, I sub x. So if you know VOC and RTH, you can find the current Ix for any value of voltage Vx. Keep in mind that this Thevenin circuit is not the actual physical circuit. The actual circuit can be very complicated, but the Thevenin circuit is, for analysis and design purposes, identical to the actual circuit, but it's much easier to work with. One really nice thing about Thevenin's theorem is that you can determine VOC and RTH from measured data. I only need to measure two combinations of Vx and Ix for the physical circuit and then fit a straight line to that data. To get my data, I set up the original physical circuit and apply two different values of voltage across the terminals. Then I measure the corresponding currents. Keep in mind the difference between the actual circuit that I'm testing and the model of the circuit governed by this equation. I don't actually build the Thevenin circuit. It's just a simple way to predict the behavior of the actual circuit. Now let's use this data to estimate the linear relationship governing the circuit behavior shown here. This is the equation relating Vx and Ix according to Thevenin's theorem. It gives Vx as a function of Ix. So Ix is the independent variable, which we usually think of as x, and Vx is the dependent variable. Which we usually think of as y. RTH is the slope. We usually think of that as m in our standard form of our equation, and VOC is the y-intercept, which we usually write as b. So this equation is of the form y is equal to m times x plus b. So in our data, Vx corresponds to our y values, and Ix corresponds to our x values. I'll use this pair of data as my first data set, so it'll correspond to x1 and y1, and this set of data will be my second data pair, x2 and y2. The equation for the slope, m, can be written as y2 minus y1 over x2 minus x1. Y2 is 7 volts. Y1 is 2 volts. X2 is 1 milliamp, which is 0.001 amps. And X1 is negative 1.5 milliamps, which is minus 0.0015 amps. So this becomes 5 volts over 0.0025 amps, which is 2000, with units of volts over amps, which correspond to units of ohms. So RTH in our equation is the same as the slope m, and that is 2000 ohms. Now we can find the y-intercept by using m in either one of these data values to predict b. Since y is equal to m times x plus b. I can solve for b and substitute, for example, y1. b becomes y1 minus m times x1. So b is equal to y1, that can be 2 volts, minus m, which is 2000, times x1, which is negative 1.5 milliamps. So b is equal to 2 volts minus 2000 times 0.0015 is minus 3 volts. And b is equal to 5 volts, which is the same as VOC. Now I've got values for VOC and RTH. So we've got the equation we want to get. We should probably check our results though. We used x1 and y1 to estimate b. Let's use x2 and y2, plug them into our equation, and see if that accurately predicts our values. Check with x2 and y2. y2 is 7 is equal to VOC, which I found to be 5 volts, plus RTH, which is 2000, times x2, which is 0.001 amps. So 7 is equal to 5 volts plus 2 volts. So 7 is equal to 7, and our results check.